is hard. And to give you an idea, Jupiter orbiting our sun causes a total change in velocity of our sun of about 24 meters per second. That is faster than a car goes, but it's a pretty fast velocity. But if we get down to an Earth-sized planet, we get all the way down to a total change in velocity of 18 centimeters per second. That is crawling. That's a crawling velocity. Change in velocity that corresponds to a crawling velocity. So I just want you to think about that for a second. Imagine a star, something 300,000 times the mass of the Earth, and you want to be able to measure whether it's moving towards you or away from you with a precision enough to tell the difference at crawling speed changes. And we're getting there. The current state of the art is a meter per second, about 10 times bigger. And there are two primary techniques to do that. So we use high resolution spectrographs. This is an example of, I forget which spectrograph this is. Oh, this is espresso. But this is the world's best spectrograph for measuring precise radial velocities of stars. The US just built NUID, and it's on the WIND telescope now as of a couple of weeks ago. And it's incredibly expensive. You basically put your spectrograph in a giant vacuum chamber, and you stabilize everything. You stabilize the temperature, you stabilize the gravity vector, you stabilize the illumination. Because any little slight change causes the spectrum on your sensor, your detector, to move. And if we're talking about velocity changes of a meter per second or less, we are talking about shifts in the spectrum of your star of less than 1/30,000th of a single pixel. Now, in our case, we have thousands of pixels. So we do the whole spectrum at once and then average down all the shifts so that we get an average shift of that type of precision. But this is basically what we do. It reminds me of the era of physics when people were trying to build devices that got closer and closer to absolute zero. Just more and more sophistication, more and more controls, more and more feedback loops, more and more shells for thermal control. It's a very similar game. Well, I didn't have a lot of money as a postdoctoral scholar, and I looked to what other people had done to detect planets. They used a gas cell. And so I built a gas cell. And what does a gas cell do? It imprints on the spectrum of the star a reference spectrum. And then if we put the light from a telescope through that gas cell before the light gets to the spectrograph, then any shifts in the gravity vector, temperature, or pressure, or illumination of the spectrograph that causes the spectrum to shift around on the pixels of your detector, well, the same thing will happen to the absorption lines from your gas cell. So you could do exactly what they tell you to do not to do in high school physics, which is to take two very big numbers, subtract them, and believe the result. But that's exactly what we do, and we believe the result. So long story short, the instrument causes the spectrum from the star to shift back and forth, and it does the same thing to the light that the gas cell took away, and then we subtract that so we have a stable measurement. Now, we built a gas cell because I was interested in operating at near-infrared wavelengths. And the visible, this was done with iodine, heated up to about 40 Celsius so that it absorbs the visible light. But can anyone think of a gas that absorbs in the near-infrared? Water. Water has one of the strongest, you need molecules that have strong dipole moments. Water, methane, carbon dioxide, ammonia. Say those molecules sound familiar to anyone? Playing a role in something called global warming and climate change? Yeah, it's because they're strong near-infrared light absorbers. So here's an animation of light of a star in red, shown at the top, small piece of the spectrum, passing through our gas cell, producing the spectrum on the bottom. And so as the star moves back and forth, and of course this is exaggerated by quite a bit, we can see the shift of the absorption lines in the spectrum of the star with respect to the absorption lines in the gas cell. And no matter where those lines hit on our detector, we don't care as long as we can subtract it off and move on. So we packed up our gas cell, and I built the first one 10 years ago in 2009. We flew to Hawaii, and everyone, I like telling this story, I tell this to everyone who talks to. I'm the only one that gets off the plane in Hawaii with a winter jacket, and people look at me like I'm crazy. Like, you're in Hawaii, why do you have winter jackets? Because we're going up to the summit of Mauna Kea, 14,000 feet above sea level, where your brain gets 60% of the oxygen. It gets at sea level, and you feel like a moron with that little oxygen. And we drive it up to the summit, and they actually turn it into a dirt road here. So we're about to hit an elevation of 10,000 feet right there. It turns into a dirt road because they don't want people accidentally dying. My very first trip up to the summit, I happened to go with one of the few astronomers who's actually rolled a vehicle off of this road and survived. Then it becomes paved again, and then we pass some snow. And then we finally get to the summit where the world's best telescopes are located, along with a few other locations like Chile. And here's the Keck telescopes. We're going to turn around there, and then IRTF will be off on the left. And so this is IRTF. It's a NASA-owned telescope, which I keep trying to tell NASA to actually use it for a test follow-up. That's another story we'll talk about, Karen, later. It's a 3-meter telescope. For scale, there's a railing on the fork of that telescope, so 3 sets of scale. Here's the gas cell that I built and integrated into a spectrograph back in 2010. I like showing this picture because this was a real low-budget affair. These are fence clamps from Home Depot. And we literally strapped a laptop to the side of the telescope to control it. So we did it on a budget, less than 50 grand. And built this gas cell, and it worked. And we used it again. We published a couple papers. And we used it again on iSHELL, which was the reason they let me mess with C-Shell, which is the predecessor instrument, was because it was getting replaced. So it was okay if I accidentally broke it. Not really, but that's what I tell myself. And iSHELL went on Sky on IRTF in 2016. And it's an amazing spectrograph. Here's the gas cell integrated into that spectrograph. Here's a spectrum of light, with white light flooding the spectrograph. And so all these little absorption lines, these missing pieces of light, are from the methane, isotopic methane, in the path of the spectrograph. And why did we use isotopic methane? Because Earth's atmosphere has regular methane. So we didn't want a nice, stable wavelength reference sitting on top of the unstable wavelength absorption of the Earth's atmosphere, and this created effectively a whole new gas. And it operates at a really unique wavelength of 2.18 to 2.47 microns out in the near infrared, where pretty much no one else is doing precise radio velocities. And we've been able to achieve, here's just a quick plot, velocity precision of under 3 meters per second. So this is time. This is velocity in meters per second, and this is the best anyone's ever done in the near infrared up until recently. There are now 2 other teams that have reached this precision: the Habitable Planet Finder on the HET telescope, SPIRU on the CFHT, also in Hawaii, and IRD is almost there, which is a Subaru near infrared spectrograph. And I think only SPIRU and iSHELL operate at this wavelength. I'll talk a little bit why that's important. But this is a remarkable result that we're really happy about. And it's great because we can now measure masses of planets that the TESS mission is finding. So the TESS mission uses a transit method. It measures the radius of the planet. And if we go and get the mass with iSHELL, we can get the density and thus find out what it's made with. And so this is just a paper showing test candidates, their brightness, and the signal that they should be able to produce. And so here it's too faint for us, and here the signal's too small. But these planets in this region will be able to measure their masses over the coming years, and we've already started doing that. And I'm here today to tell you about one of those discoveries. So over the past few years, since we built iSHELL, other people have been interested in finding planets around other stars, and we've been able to directly image newborn planets. This is a two-planet system called PDS 70BC that was discovered within the last 2 years. Here's a planet found around the T Tauri star, a CI Tau, found with the similar velocities, but look at their axis here. Instead of meters per second, this is kilometers per second. I don't believe this result, no offense to the authors, but this is potentially a hot Jupiter. And they found several transient planets. I was a member of this team that found this transient planet orbiting a star in Orion. And this one, we still aren't convinced is real yet because the transit shape changes as a function of time. We think the orbit of the planet might be precessing, but it's a very bizarre system. And this one was just announced this year, a very active star. So this is the brightness of the star taken with the TESS mission as a function of time. And you see the brightness going up and down, and that's due to spots on the surface of the star rotating into and out of view. But sure enough, at different times, we can see different events here where there was a brief dip in brightness. And this is DS-B. This happens to be a planet that's around 20 million years old as well. It's going to be a real fascinating system to follow up, discovered by my colleague Elizabeth Newton. So she got her paper out